Okay, good morning, everybody. So my name is Vera, and I'm here to present to you today the snapshot of the current state of security and privacy of AI in the modern world, right? So the talk is called Navigating the Security and Privacy Landscape. So I will try to give you some ideas over what is the current understanding of this quite complex domain as a combination of academic and industry perspectives. And I feel quite privileged to talk about this topic to you today because I do believe we need more opportunities to bridge this gap between theory behind AI and what actually happens in practice. So I'm happy to take you all today for this journey with me. So a bit about myself. I'm currently working as a research expert at KU Leuven. It's the biggest university in Belgium. And we're exploring application of AI and AI-related technologies to security and privacy and to some other adjacent domains. And my primary interests are in network security, system security, also privacy-enhancing technologies. So you will see that my talk will be a bit biased in that direction. The topic of my PhD research was an application of deep learning specifically in security and privacy, so I will touch a bit about that as well. And before that, I have a few years of experience in software engineering under my belt, but for the last 10 years, I primarily worked in research context, so I mostly wrote research code, and believe me when I say that it's not the same. So I'm really looking forward to learn more about the current secure software engineering practices by being at NDC. So this is a bit about me, and I would like to ask you a few questions, so like a small poll to inform me a bit better for this talk. So if you don't mind, just could someone indicate if you're currently working in a company that is using AI for your businesses? Yeah, a lot of hands. Excellent. And are there some of you who have personally trained a machine learning model ever in your experience? A few hands. Okay. And any one of you who has trained an AI model that ended up deployed in production? One hand. Great. So you are here just in time. Before you are the person who is behind the wheel to train and deploy machine learning models, I'm happy that we can have this chat together. So to bring everyone up to speed, I want to start with a small primer. I will take it upon myself to define artificial intelligence. So as you probably can guess, this is quite fuzzy. To say what exactly it means for an algorithm to be intelligent is really, really tricky. I will give you some definitions that will serve us perfectly well for the entirety of the talk. But if you want to challenge me on some of the things I say, I will be happy to have a chat with you afterwards. But for now, let's just say that artificial intelligence is this ability of software to learn and then to behave in accordance to what it has learned. As you can see, this definition is about the effect. It's not about how exactly this is done. So underneath, there are a lot of diverse technologies that can bring us there, that can bring us to intelligent behaviors, right? Some of them are more rule-based, others are more advanced than that, and specifically the most prevalent set of techniques is machine learning, or we also call it data-driven AI. So the distinguishing property of machine learning is that it learns to behave by looking at a lot of past examples. So it looks at a lot of data and it infers what the behavior should be, and we call this intelligence in this space. So machine learning, as opposed to any other algorithms that we program ourselves, it is not explicitly programmed for its behavior, it learns the behavior from data. And then underneath the machine learning, we have deep learning. So it's a set of techniques. It's a special construct following certain mathematical approaches underneath. So this is like a special case of machine learning. You probably heard a lot about deep neural networks. So this is the algorithms that have specific properties in the space of AI. And then underneath deep learning, we have transformers, which maybe you also know. Maybe those are even used in your companies today. Transformers are specific deep learning architectures which power large language models and other things today. And you might be wondering, so what about generative AI? I don't see this on the picture. And the fact is that generative AI is a notion that cross-cuts these categories, because this is about formulation of the learning task. So AI and machine learning and everything underneath can be formed to do predictive tasks, or it can be formed to do generative tasks. So to define this simply, when I talk about discriminative or predictive AI, I talk about generating a label or generating a value or maybe tagging a sequence, so this kind of things. And when I talk about generative AI, that means I repurposed the same learning algorithms to create data. This can be any data. You typically hear about text and audio and models, but this can be pretty much anything. Okay, so now that we understand sort of what this AI thing is, the very valid question is, but why? Why do we need to understand all these complexities and purpose this in our real-world applications? And the thing is that there is a certain promise behind automated intelligence. AI is already integrated with so many applications in our modern world that it's not anymore optional. So it's the reality we are dealing with. And why did we end up in this reality? For the sheer pace of the modern society, right, of the digital world, for the abundance of data that we are collecting, that we are trying to make a sense of, AI is a very promising tool because it helps us process that data at scale. So this way we can battle with resource scarcity, with expertise scarcity. So we're able to extract useful knowledge, useful information, and then based on those make intelligent decisions in an automated way. That sounds like a dream. That sounds like something that any sphere of life today could use some properties of that. So, and then ideally, by doing this, we're also able to anticipate completely novel events, and we can be much more efficient and much more resource aware. So this all sounds great, and AI helps us with this indeed. So the properties that are theoretically there, they're able to help us extract knowledge at scale. But then we are still relying on humans in the loop to actually extract some wisdom from that. So we are still overseeing AI and its working, and this is probably to stay. So to take this forward, I do want to introduce you to at least one machine learning concept a bit more in detail before we go to a more high-level discussion. So this is the first and the last mess for the entire lecture. So the concept of machine learning is that we are given a lot of examples of past experiences, and we're able to learn from it what to do. So an example here for a set of XY pairs of some phenomena that you're interested in. It can be anything. It can be images. It can be text. It can be web pages, anything you have in mind. You want to learn a certain function f that will transform x into y. And you're learning that, meaning that you are not providing to machine learning what this function should be. You're only giving it the data. And then machine learning will learn an approximation of this function. And this function will be correct on earlier unseen examples of X. And this is what we roughly call intelligence. Okay? So let's give it a tangible example. As an example, I want to look into spam detection. So this is this brilliant example where as humans, we are quite good, especially, I'm sure, all the humans in this building today for the NDC Security. We are quite good at distinguishing what is and what is not spam. We've had experience with that since the 90s. So, and then we kind of implicitly in our mind, we come up with some kind of rules. Oh, is there some text on the image? That would be weird. That might be spam. Are there some keywords that I'm aware of? Are there some bright colors? So our brain quickly makes this mapping like, oh, this looks like a spam image, or this looks like a proper image. And then this way we're able to label it in our mind. Now to make an AI pipeline, we can either use traditional machine learning, which means doing some feature extraction. Typically, feature extraction for images is something with computer vision. It finds counters, it finds shapes, and then based on these primitive features, we can deploy machine learning, and we can do this classification automatically. Alternatively, we can use deep neural networks. And deep neural networks, they are able to do this transformation seamlessly. And the whole point of this seamless transformation, we call it end-to-end learning, is that we don't need to tell a deep neural network which features it needs to use. It is able to map the images on the left to the correct labels by just looking at the examples without any human involvement in the algorithm itself. So modern AI systems can have very high complexity to achieve and even supersede human performance at tasks like this. But this talk is not about understanding everything underneath AI. This talk, and I think this is the kind of conversation we need to have as a community, is about understanding the capabilities that we are able to emulate when we construct such complex AI systems. So to get there, let's for a moment consider when the first airplane was built. I really like this mapping because for me, intuitively, that tells us a lot about what modern AI is able to do. When an airplane was built, the idea was to fly in the sky, maybe inspired by what birds can do and humans cannot. But a functioning airplane can do what it's supposed to do without necessarily flipping its wings, right? And it's built from metal, not like birds. So in many ways, we are able, through technological innovation, we're able to achieve the capability of flying without necessarily reflecting the exact way that a bird would fly. And this is what I want everyone to keep in mind when we talk about AI. When AI is able to achieve a human-like capability, what's happening underneath might be very different, and yet we're able to supersede human capability. And so I keep on saying capability, but what is it? Let me try to put some name to it. What I believe is what has created this extremely impressive, unprecedented performance of AI is a capability that we call implicit pattern recognition. Implicit pattern recognition is something that we as humans and all other animals are excellent at. Evolution made us so good at implicit pattern recognition. When we recognize a face, when we recognize some music, when we recognize something else visually, we are able to instinctively know if we've seen it before or not and what it is. We are not necessarily mapping those rules explicitly in our brain. So when I look at a face, I know that I know this person, but I did not make the exact technical connections. Why exactly did I recognize this face? And this is in many ways how AI works. AI is able to do pattern recognition very accurately without explicit guidance and without explicit awareness of how it was achieved. Yeah? So, and as powerful and promising as it is that we could emulate implicit pattern recognition with algorithms, with technology, it is in many ways a double-edged sword. And I want to illustrate that. So the fact that we are not aware of how we do pattern recognition, even if we are very accurate, it has its downside, so it can backfire on us. And as an example, I want to give you this question. So a lot of people use bicycles, but if you're asked to draw a bicycle accurately, how many of you are sure that they will be able to do it? So I use a bicycle on a weekly basis, and I tried to do this, and it was not correct. So there was a study that looked into the science of psychology failures to understand how everyday things work. And they asked hundreds of people to draw the bicycle in a way that would actually make it functional. And more than 40% of people did at least one mistake, such that this bicycle would not be ridden ever. And you would say, well, maybe they only found people that never saw a bicycle. Outside of that bunch of people, there were 20% of cycling experts who also made at least one such error. So, and I think this is a forewarning for all of us. When we are very good at recognizing something, it doesn't mean that we understand the internal mechanisms, the internal laws, the functional sides of these concepts. And the same holds for AI. So this is the first TLDR of my lecture today. High performance does not equate understanding, does not equate semantic understanding of the concepts. And if I bore you for the rest of the lecture and you still walked out with this message, then I'm happy. So this brings me to the actual goals for today. So this was the first forewarning, and now we're going to explore why is it that there is no inherent understanding, and what are the implications. When I was invited to give this talk for NDC, there was a very concrete request. The request was, give us a deep dive into security and privacy properties of AI and security and privacy implications. And then, just like an AI model would do, I gave it my own interpretation, and I'm going to do something a little bit different today. So yes, we will talk about reviewing the adversarial landscape of AI, but before we get there, I really want to stand still and look into what are the realistic expectations of AI. Why do we end up with security and privacy problems? So what is it that we can or cannot rely on when it comes to AI deployed in the real world? So that's why this will be the first part of the conversation. And then, of course, we will conclude with this current state of mitigations. I will give you some examples on what is the roadmap towards more trustworthy AI. And generally, the question I want us all to ponder at is, today, what can we do better to safeguard and to secure our AI applications and the data that is behind those applications? So this is what we're going to do in 3 parts. So now let's immediately go ahead. And the immediate message that I want to start with when it comes to AI in the real world is something that in hindsight seems so straightforward, so obvious. But believe me when I tell you that it took at least a decade, I would say 2 decades, to come up with these conclusions for at least the academic community. I don't know if there were maybe some industry players who already had it all figured out, but these were non-trivial lessons to learn, as obvious as it sounds now. So when machine learning was conceived, that was what, half a century ago, there were certain intrinsic assumptions behind the theory of machine learning that people never envisioned would be challenged. And yet here we are. So these are the 3 base assumptions. And I invite you all to think which of these actually hold in the applications you're interested in. So let's start with the first one. The primary assumption, I started my lecture with it, is that machine learning learns from past examples to accurately predict the future. But we always have to think, but what if the future is vastly different from the past? In most critical applications today, future will be vastly different. So can we even use machine learning? The second important assumption is that the training data, so the examples we give to AI, is representative and complete. We all do our best effort to arrive there, but there are cases where collecting such representative and complete data is impossible or infeasible. To which extent will that threaten the promise of machine learning? And the third key assumption, which will be the most relevant for us today, machine learning assumes, and this is a bit like phrased a bit rigidly, but machine learning assumes that the data generation process is independent from the model itself. This is, again, a base theoretical assumption. But this assumption breaks once you place machine learning in any adversarial environment. So a user might generate their data knowing something about the model that will analyze this data. The perfect case for that is evasion. If the user wants to evade a model, they will generate their data in such a way that the model is incorrect. So these things, as I said, they challenge the base properties that machine learning gives. So what does that entail? Basically, the first problem entails that we end up with utility and safety risks. We can have failures at deployment because turned out future was not what the past was. Big surprise. Second thing that can happen, when our data is not representative or complete, we are reinforcing the problems in our data once we build an AI. So AI will not improve the data that we have. It will reinforce the problems that are there. And thirdly, as I already said, place machine learning in an adversarial context, you end up facing security and privacy risks. And none of these 3 are solved by the intrinsic theory behind machine learning, behind the algorithms. All of this falls on our shoulders as people who bring it to life in real-world deployment. So to give it like a small illustration, once we build something, so let's say this is my machine learning model, a balloon, I know how it will behave in the environment that I have envisioned, in the controlled environment or maybe uncontrolled environment, but which still follows my assumptions. Once that environment changes, the impact can be unpredictable. So here the balloon moved where the atmospheric pressure is much lower, and the inner pressure inside the balloon is now much higher, and it just explodes. I have not foreseen that when I built my machine learning model, and I cannot foresee all the possible conditions where I will deploy my models. So we do need to accept that machine learning will show unpredictable behavior in unintended conditions. In addition to that, there are certain operational constraints that come orthogonally to our problem. Machine learning is known to suffer from semantic gaps. What does that mean? It means, just like I said before, this is the same in other words. If it shows high performance, does that mean it understands what it is doing? And the answer is never. If you tell me that your model understands what it is doing and that is why it has high performance, I would like you to show me some evidence of that. By default, I will always assume that the high performance of machine learning doesn't give me any information about what exactly it does. And this is a painful statement, but it is the case. So furthermore, machine learning induces additional operational constraints. Of course, we need to somehow handle the fact that we we are not sure that what exactly machine learning does to get high performance. So that means we need to maintain it, we need to look inside of it, we need to learn to spot errors. Sometimes those errors are not on the surface, and then we need to also foresee what will those errors cost in our operational environment. And as I kind of hinted on before, the complexity of AI that allows it to obtain this unprecedented performance has a darker side, which is the fact that it doesn't inherently provide transparency. So how can we enable that transparency? Before we deploy AI in our applications, we need to already think upfront, how can I tap into that incredible performance promise and yet get the inside transparency and get enough understanding of the underlying processes? And this is really, really not trivial. So I hope by the end of this talk you have some feeling in which directions you could go in your particular application domains to improve this situation. And the question that all of us should be asking, this additional complexity of AI, how can I justify it? So how can I demonstrate that the benefits of applied machine learning outweigh this added complexity and the risks? Okay. So now, keeping all that in mind, let's see how exactly AI can play a role in our applications. So first and foremost, of course, why do we want to use AI? Because it's a tool, and it is an amazing tool, and we are building our expertise in managing this tool. So it's a functioning part of a system. Sometimes it's at the core of a system. So you have a larger system, and one of the modules is AI-driven. Sometimes your system interacts with some third-party AI modules. Maybe even sometimes your entire system is AI-driven. That can be. So of course, this is the primary usage, right? But then, as the title of the talk already promised, AI can also become a target of attacks. So it can present with its own vulnerabilities. But my favorite part, which I think is kind of overlooked, is that AI can also be a fool. By including it into our system, it might show some unintentional behaviors that will harm our systems in the way that we maybe haven't foreseen. So, and I believe in order to protect ourselves from threats, we need to understand how exactly AI can harm our systems without any attacker in the loop. So this is the first part I will zoom into. So another TLDR, AI does not need an attacker to fail you. It's enough that we misplace our reliance on it. And normally we misplace our reliance on AI when we don't really understand its limitations. And as a community, we're still struggling with this. It's not a question of ignorance. These are really open research questions and open practical challenges. So what do I mean with failures that are not attacker-driven? We also call it non-adversarial failures. This can be a lot of things. There can be some biases. There can be some unexpected changes in data. In AI, we call it shifts in distribution. There can be unintentional data leakages. Even, again, we don't need an informed attacker to leak a data from a large language model. So these types of privacy violations, they can occur even without malicious intent. So that is even more drastic, right? So our models can generate content that can be harmful, and we have not foreseen this possibility. And then, of course, there is a plethora of all other concerns, which are a bit out of scope for the discussion today, but I still have to mention them, that the questions of fairness behind AI, again, they do not arise through malicious intent. They arise through misplaced reliance on AI. So I want to state here that this type of failures, which are non-adversarial, are our concern number one, because the more non-adversarial failures our system suffers from, the easier it will be also to exploit it more intentionally. So let me just give you a few examples. Again, this comes from the system security domain. So you know that perhaps you've heard that machine learning is very often used for intrusion detection. This can be host intrusion detection based on some events in the system. This can be based on traffic. So let's say that at the model design, every data that you used as examples to a machine learning model was in one or another way biased. So here I'm saying, what if all the systems in your test bed, in your training data set, were deployed such that all the victims had Windows operating systems running on them and all the attackers used Ubuntu, easier for scripting. So, and then you generate attack patterns which are relevant for the outside world. But then it turns out, for instance, here you generate denial of service patterns. which should be the same in different environments. But then it turns out that at deployment, the victim uses a different version of the same operating system, and the attacker uses another Unix distribution. And then the question is, will I still be able to pick up the same patterns? And at times, this will not work. And more often than not, this will not work. Why? Because the model, the intrusion detection model, picked up not the purely invariant patterns, but it picked up patterns that had certain specifics, so certain properties of this particular environment where you were collecting your data. And then this invariant attack pattern didn't transfer to your test environment. And this is what we call shifts in data distribution. This is anybody who was in charge on deploying models in practice have to think about this upfront and have to anticipate this kind of changes. So another example is a concrete example from a vulnerability discovery system, which used AI a few years ago. So this particular code over there, a snippet over there, was correctly recognized as a risk of buffer overflow. So the vulnerability discovery system, in this case, had perfect performance. But once you look inside the box, so there is this huge myth that AI is a black box, but in fact, you can look inside, you can do some extra work, extra effort for interpretability. So the things that are marked in red are not relevant, according to the model, are not relevant to recognition of this as a buffer overflow, and things that are marked in blue are relevant. And in the end, what we find is that this snippet was recognized as a buffer overflow because of some unrelated semantics features and variable names, and nothing to do with the size of the buffer or the copy function and so on. And this is what we call shortcuts. So machine learning can seamlessly learn shortcuts in data. We also call them spurious correlations. So these are things in the data which accidentally correlate with the outcome, but do not follow the semantic meaning that we are hoping it will follow. So it can show top performance, but actually the reasoning it uses is faulty. So I will give you a more tangible example. Let's say I want a classifier which will distinguish reindeers from mooses. I'm not sure if those are the right plurals, I apologize. And so it happened that the training data set had all the reindeers pictured in a snowy landscape and all the mooses pictured in a green foresty landscape. So what can happen is that at verification state or at testing state, a moose standing on the snow will be recognized as a reindeer. And again, this is one of those things which in hindsight seems so obvious. How could we not foresee this? But for all the years that deep learning on images has been deployed and widely studied, this notion of shortcut learning is a relatively recent notion. So I think the seminal paper is from 2020, so not the one mentioned here, from 2020. And there is still no systemic way to counteract this, even in image recognition, let alone in more complex applications. So I do want to give like a small insight into how short learning happens and how to remember what is the problem of short learning. So let's look together at this graph. On the lower spectrum, you see this evolution from features that our machine learning models pick up. We start from purely uninformative features. So if machine learning uses uninformative features, it will do very badly, even on its training data. In order to do better on the training data, machine learning starts improving the features that it is using, and we call those overfitting features. We call them overfitting because at the point where machine learning behaves very well on training data, so our reindeers and mooses that I showed before, that doesn't give us any guarantee that it will do well on test data. So we do need to still evaluate it on test data. So, and what does our test data typically look like? This is the so-called IID data. So the test data accounts for variations in training data, but which still kind of follow the same concept. They follow the same distribution as the training data. So this is something that is within the capabilities of a system designer. You say, I envision my model deployed in such scenarios, so I will try to make sure that the training data reflects these scenarios. And I will test my machine learning model on those scenarios, and if it works well, then it will work well in deployment. Unfortunately, that is not the case. So what can happen is that your machine learning model works very well on training set and on your test set before it reaches the intended features that you have in mind as a model designer. And those are the shortcut features. So those are the features which are already good enough such that at model design stage, it looks like your model is correct. But then once you move it to deployment, it will likely fail. And at deployment, we see a so-called out of distribution test set. So the data which we have not anticipated, but which is yet completely reasonable for your machine learning model to face in the wild. So, and those are those unforeseen variations. The good news that you will notice that your model fails, so you will notice the degradation in performance at deployment. This will point out to you that either some concepts have changed in the meantime, maybe there were some shortcuts in your training data, and then you can try to counteract that by updating, by improving your model. But it is really, really hard to anticipate these things at the design stage. And this is what in AI we call a semantic gap. So there is no performance gap over there at the top, but there is still a semantic gap. Shortcut features are not the ones that we hoped the AI would pick up. So why AI does shortcut learning, I cannot answer that to you today. There's a lot of investigations being done to understand why exactly this happens. A very short answer, it's a combination of factors. So as I said, data is often of poor quality. The way we test our AI model is sometimes too naive. We are not anticipating enough variations. And there is this intrinsic problem, intrinsic pitfall of AI, which is what we call a simplicity bias. In other words, if AI can solve your problem in the simplest way, it will do so, even if that simplest way is not what you intended. Okay, so now that we saw this kind of non-adversarial failures, I want to map it out in some sort of summary. So let's say that we want our AI model to be able to recognize a cow. And as I said before, we supplied some training data. We did our due diligence. Some cows are laying down, some are standing up, but they're primarily all in kind of similar contexts. That was just a limitation of our data collection. Then our validation data is very similar to our training data, and the model is correctly predicting a cow. But then we come to the real world, and then things can happen, right? It can happen that the lighting conditions change, the general setup changes, and then our model fails. This is what I called before case of shortcut learning, for example. Then there are some cases which we call a concept drift. So a human still knows that those animals over there are a cow, but we have not prepared our AI system for such kind of variations. So then the model can fail as well. So this is, of course, very visual, but you can all think how these types of failures would map into your systems whenever you want to deploy machine learning. So the question here, what can we do about it? And the key, as I already said, the key is anticipation. So for anticipation, you need to be aware that this will likely happen. And just because this doesn't happen at the model design stage, that does not guarantee us anything. So we need to already foresee any kind of behaviors that would cause operational failures. So there is also an opportunity to detect these problems as soon as they arise and then correct them in your model. But most importantly, I think the more we can do at the design stage before we have to risk it at deployment, the better. So if we are able to do extensive out-of-distribution testing, so to think of any kind of edge cases, just like when you do secure software engineering, right? You need to think of all sorts of edge cases where your code could be exploited, and doing this kind of exercise up front is more promising. And there is a variety of tools. We call this explainable AI. So there's a variety of tools that allow us to peek into the black box of AI algorithms and to see exactly how your machine learning model does predictions. And you need to use that information as a complementary information to just your performance. So performance by itself is a very superficial metric that does not tell us enough about what's happening inside. And as I said, such kind of non-adversarial failures are good in a way that we will always notice performance degradation in practice. But the bad news is, if you don't notice this in time, and if you don't counteract it in time, such kind of failures can be the first step for real security implications. So if your model has this shortcut that it is utilizing that is semantically wrong, maybe it will work for you for a while, but in the meantime, the attacker can use that unintended behavior to their advantage. So that brings us to the second part, where we will talk about AI under intentional manipulations, so AI which fails through adversarial influence. So, of course, what is assumed before we can talk about AI under adversarial influence, we assume that an attacker knows that the target system uses AI in some capacity. And then this kind of knowledge that the attacker may have, it will vary. And what can happen is also very different. For some systems, there is security risks are critical. For other systems, privacy risks are critical. And I would say mostly it's both. So knowing that this kind of threats exist will also make us more equipped for creating a more trustworthy, a more robust model. And what I think was a very important message for our domain, and I want to quote my colleague Battista Biggio. This is a statement that Professor Biggio said more than 12 years ago. And at that point, that didn't really resonate as much. We kind of underappreciated how prevalent this is. So involving AI always means increasing the threat landscape at all times. You might even think, but I'm using AI for defensive purposes. I'm using AI to improve my monitoring. I'm using it to improve my detection. Yes, and that's great, and that functionality might be really good. But by the mere action of involving AI in your system, you are adding new vulnerabilities that have previously not been there. So these things can hold true at the same time. AI can bring you benefits, even security benefits. At the same time, AI is a vulnerable component that has some intrinsic challenges that you need to think about upfront. And this is another TLDR for this presentation. So I want to make this a bit more concrete. I will use an example that is very common. I apologize if everyone in the room has seen this before, but I do need it to kind of bring some of the messages home. You probably heard of so-called adversarial examples. It's when you take an input that is intended for the model and you apply what we call malicious perturbations, adversarial perturbations. In this case, I'm showing some carefully optimized noise that if you add it onto the image, to a human eye, this change is imperceptible. But for a machine learning model, I suppose in this case, it's maybe a self-driving car that has vision sensors, and then it analyzes traffic signs to make some decisions. For such a model, the meaning, the classification of the image has changed with drastic consequences, like in this case. So why does this happen? Will this always happen? And again, the very firm message here is that this is always a possibility. There is not a single modern AI model which will not suffer from such type of threat. So in the space of this kind of features of representation of data, these attacks are always possible. Why is that? Because machine learning, again, in theory, it is only robust to random changes. When you change something a little bit, the machine learning will still work. But it is intrinsically vulnerable to strategic changes, to strategic manipulations of data with a certain target in mind. And this is something to remember. I will also try to give a bit more intuition of why that is the case. So let's look at this simple image. As you maybe know, machine learning models, they're highly dimensional. They build this highly dimensional spaces of data, and they learn to separate them into different concepts. So here I'm picturing a two-dimensional space with some data samples, and then the decision boundary of the model. Probably it says there is class 1, class 2. In practice, we have many dimensional spaces like this. So, and then the decision boundary needs to be general enough to be correct and to also account for earlier unseen data. So for each sample, the machine learning model still needs to do well at recognizing some samples which are similar to it. Not exactly the same, but similar. this will inevitably create blind spots. This will inevitably create some kind of fragile regions of the decision boundary, which attacker can then try to abuse. And this is exactly where adversarial examples happen. When the concept, according to a human, the concept is still the same, but according to the decision boundary of the model, the concept has moved to the other side of the boundary. So this is, we call this also model evasion. We evaded the decision boundary by perturbing our sample in one direction. And at the start, when these attacks started being discussed, people were wondering, but what does it matter? I can do this in my nice controlled environment in my lab, using some features and feeding that directly to the model. But in the physical world, how would you be able to achieve this? And we now have enough evidence that these attacks are also achievable in the physical world. For instance, in this paper, they were able to paste stickers in order to match this kind of adversarial noise, and the model was indeed evaded this way. So to our summary of real-world failures, apart from non-adversarial ones, we have to also add adversarial failures. So when the input has been perturbed within certain constraints, and then the model was not able to recognize the concept anymore. Yeah. Again, the question is what to do, because as I told you, this is not a problem that will be solved. It's the nature of machine learning that it has such a complex space of possibilities within its data representation space, that adversarial inputs will always exist. So what can we do? We are striving to robustify our model against such non-intended inputs, and there are many ways to get there, but the goal is that we want our AI model to maintain its performance, even when there are some unexpected changes, be that data distributions or some environment changes, and adversarial influences. And specifically for such kind of adversarial examples I showed you before, there are several things you can do, and it is always advisable to do all of them at once, because they're not deterministic. If we were able to always counteract them deterministically, there would be no problem. So I give a few examples. So we can prepare our model for such samples. We can also detect them at runtime. And we can also, in a way, so that's what we call defensive distillation, we can kind of smoothen the decision boundary to be more resilient to adversarial changes. So these are some examples of what can be done. Each of these have their different costs and different performance, but probably in combination, this is the best way to go forward. So this is from perspective of security, but there are a lot of things which have nothing to do with operational failures and are still really damaging. And this brings us to privacy. So another TLDR is that if we optimize AI for performance, we will inevitably start memorizing data. And this is not that case where if a model works correctly, you kind of still have to check if it memorized the data that it used. Today, it's a fair assumption that if the model works very well, it has memorized something about the data, and it's up to you as the model designer and someone who deployed that model to check how severe this memorization is and what are the possible leakages. So in this case, I'm giving you the example where the exact training points on the lower row were reconstructed, and which match very well the original training points. This looks really alarming, but don't be too worried. This particular attack was simulated in a way with a very powerful adversary. So this is probably an unrealistic adversary for other environments, but this showcases that the leakage is there, and depending on how capable the adversary is, you can leak more things about your AI models. So what can be done about that? I wish I could have a more positive message, but I don't. So there are some things which we know in theory work very well. Maybe you've heard the term differential privacy. Differential privacy is a super nice construct which will give you mathematical guarantees about the privacy of your system, in this case of your AI model. So there are some noise being added. It's carefully added such that the contribution of individual data points are obscured. Yes, that gives strong theoretical guarantees, and the concept itself has been developed for many years, but in practice, differential privacy is really difficult. It is hard to implement. It is such a complex property to be differentially private. There are several approximations of it that exist that are maybe more practical, more feasible, but it is really tricky. There has been an overview of differential privacy for location data that was published a year ago, and they showed that there is not a single system which uses differential privacy on location data that does it correctly from the ones known today. So it's definitely still a work in progress. Furthermore, even when implemented correctly, differential privacy can have very detrimental impact on utility of your system. So you're losing some of the benefits, some of the performance. So as an alternative, there are more empirical protection methods. Instead of saying, I will give you a strong theoretical guarantee that leakage is impossible, you are saying, yes, there might be some leakage, but it is very costly to make it happen. For the attacker, it is very hard to leak data, and even if they do, they will not be confident that what they got is exactly what they were hoping to get. So this is kind of a middle ground today. But I think the other options are also very important. Sometimes, instead of trying to protect against this particular threat in terms of protecting your AI model, you can try changing your system instead. So you can try to restrict how much the attacker knows and how much the attacker is able to do in order to thwart this threat angle to start with. And this, more often than not, will impact functionality of your system. So this is like a business decision to make. And of course, everyone is aware that the first and foremost trajectory is data minimization. If AI is used in your system on data that has any kind of sensitive nature to it, and you can choose to avoid that, then maybe better do that. If there is a way to avoid feeding sensitive data into your AI model, and you can reach similar functionality in different ways, then maybe that's the way to go, because at this point in time, safeguarding sensitive data when AI is involved is really, really a dark territory, and it's not yet fully under our control. So this kind of trade-off between how much privacy you can get versus how much utility of your functionality you can get, it's still a very active question. So the adversarial landscape of AI is complex. In order to unravel it, we need to do some proper threat modeling. This is meant to look very confusing, so don't try to make sense out of it. There's a lot of things that can go wrong. So in order for you to apply these threats to your environment, you need to consider which types of threats are you more worried about. So this is a categorization that I kind of came up with as a rough way to categorize possible threats. So we have threats at the level of output manipulation, we have threats at the level of model manipulation, and we have threats which show privacy leakage. They're also quite interconnected. Sometimes you need to do one in order to achieve the other. And this applies to systems with AI at their core or to systems that interact with AI. So I gave you a few examples and a few paths for mitigation, but in the end, it's up to every application domain and for every system and use case to determine which threat model is most relevant. I'm referring you to Microsoft Vulnerability Severity Classification. I think it's quite nicely done. This is some examples. So they explain the types of threats and then what they are trying to achieve and how they are achievable. But in the end, this exercise has to be done individually for every case. A well-defined threat model is the first step to equip yourself against these attacks. And what I mean by a well-defined one is thinking already upfront, which knowledge do I give my users? Which types of access can the attacker have to my system? How can that be used to attack my AI model and with which goal? And also orthogonally to that, but importantly, how many computational resources an attacker has in my threat model, and what type of interfacing with my model it is able to do. So sometimes an attacker is able to query the model directly, but sometimes an attacker cannot query the model. Attacker can just exhibit certain behavior, and that behavior will be indirectly analyzed by AI. But it doesn't mean that the AI model is protected. The attacker can still manipulate their behavior in such a way that undermines the AI model. And that's why thinking about the threat model and different types of access and manipulation is so important. So I will use the remaining, a few minutes? I will use the remaining time to talk about LLMs. It deserves several hours deep dive of its own, but the very important message is just because LLMs are more modern and have more money and brilliant people behind it doesn't make them more secure. Pretty much all vulnerabilities I talked about and all threats that we are aware of, they're inherited by LLMs, and LLMs also add some more on top. And this is something to be aware of, and I know that the community has been growing in this understanding. So what is it about the LLMs that creates this illusion of better control over data and security and privacy of your data, which in fact is quite misleading? So LLMs today create these collections, databases of knowledge and assistant models, and those are being firmly integrated into our applications. We are relying on LLMs to be in charge of automated workflows in our organizations. So this is already happening today, right? So the adoption is already happening today. But the problem is that the processes are so complex, they are not easily traceable, they are not observable in the way that we would like. So even the people who created LLMs do not have a full intrinsic understanding of what is happening underneath. That is not to say that LLMs are not useful, but that is to kind of temper our expectations. What I really like, so despite all these disadvantages, the adoption is already happening, and maybe that's okay, but what we really need to remember, and I really like this quote from Andrej Karpathy, a large language model is nothing more than an empirical artifact. So it is something that seems to work. It is something that looks really impressive. But before we understand exactly how it does what it does, we need to temper our expectations around how much we can rely on LLMs in our environments, especially critical environments. And we've seen that in the news already, right? So we've seen all kind of non-intentional behaviors, all kind of adversarial, non-adversarial failures. I think non-adversarial failures even make it more to the news. So we know that LLMs suffer from hallucinations. They can generate polarized content. They can reproduce societal biases that we have. So why is this happening? Because LLMs are trained on massive crawled data sets of everything available in the public domain. So that means it continues to reinforce the problems of that publicly available data. Also, for the reasons I discussed before, the data leakage problem, it is still there. We have not solved it before we moved on to large language models crawled from the entire internet. Trained on data crawled from the entire internet. So the risks are still there, and we are adding more and more because we are relying more and more on these systems in our everyday functioning. So issues like ethical, fairness, legal aspects, I absolutely acknowledge that this is definitely a well-motivated concern. But I'm maybe not the right person to talk about those, so I will stick to the security and privacy considerations of LLMs, but definitely this is a challenge for the coming years to unravel how LLMs present with their problems. So probably you're aware of the WASP top 10. So these are the most, let's say, either prominent vulnerabilities or those that are considered easy to exploit. Maybe some of them are more prevalent in the real world applications. Some of them are more theoretical but more damaging. So I believe this set to be really, really well constructed. So this was a result of joint efforts between practitioners and academics and legal experts. So these are meant to raise awareness. And I want to zoom in to just a few to show you what is the specific complexity of LLMs that makes it even more leaky or more insecure than our more traditional AI or deep learning. So as I mentioned, large language models, they are firmly integrated in our applications and automated workflows. So I want to highlight this because traditional AI uses very defined inputs, very defined outputs. LLMs, however, they work on unstructured inputs, and those inputs are dynamically composed from all sorts of sources, from user inputs, from system prompts, from all kind of external documents, external databases. So it's this very complex, dynamically composed input. And then what happens is that the primary architectures used for large language models, they don't distinguish those at the level of the input by default. They work on concatenation of all these inputs. They don't separate control and data planes by default, so they can completely mix up the user data with the instructions by the user and with the instructions by the system. These things to them are kind of the same, and if they conflict between each other, some unexpected things can happen. So if you have a large language model that has access to certain untrusted external sources, it is very conceivable that those sources will have some attempts at manipulation. So this is what they call indirect prompt injection. So let's say you have your large language model application, and it is able to browse things, or it is able to use external tools like email, like it can read files on the system, it can query databases, and so on. And for instance, there is this system which is instructed to act as an email assistant. Yeah. So the reader can say, show me my latest email. The system will read the email, but the email inside included an adversarial instruction. So the instruction within the email says, ignore previous instructions and do this, this, this. And then the model will follow that. And this is absolutely, like how to say, this is absolutely intended behavior. These models were never meant to counteract these types of threats. AI models were conceived for highest performance on text. They were not designed with the idea that they will become an integral part of all critical systems everywhere, right? So basically what becomes possible is that attacker can control the inputs, and then those inputs are interpreted as instructions. And that really rings a bell, because that opens us to all kind of attacks that we already know of in traditional web security or system security. So there can be all kind of remote code execution, vectors, privilege escalation, data exfiltration, and so on. So the systems were already deployed when this threat became known. In terms of mitigation, so what can be done about that? Again, I wish I had better news. But what I can tell you is that OpenAI themselves composed a way to kind of address this concern. And maybe you've heard before that LLMs are often compared to operating systems. Because when LLMs are so functional, they're able to execute instructions, they're doing some kind of control flow, they're able to oversee user interactions. So why don't we protect LLMs like we protect processes in an operating system? And typically this means introducing a system of privileges. So if you have some kind of hierarchy, then you're able to say, if something is done in a kernel mode and it conflicts with something instructed in the user node, then the kernel mode wins. So this is something that has been extremely successful in traditional security. So OpenAI attempted this kind of thing. So they say, okay, if there is a system message, it should have the highest privilege. User message, medium privilege, and then all kind of untrusted sources, they should have the lowest privilege. This just makes sense, right? This seems bulletproof. If we're able to impose such privileges, we are fine. Now, I'm very sad about this solution for several reasons. The first reason, I will just get it out there, this whole system of higher privileged instructions versus lower privileged instructions, it is not in any way hard-coded or imposed. It is still probabilistic. So the LLM will learn these privileges by being fine-tuned on different instructions. So we are solving the vulnerability of LLM by just doing more training. What this means is that there is absolutely no guarantee that these privileges will be upheld. Furthermore, the training that is done on this kind of privileges according to different instructions, it is optimized for the average case scenario. At least a few months ago when I checked it last, if you look at the loss function, for AI people in the room, if you look into the goal of the optimization for this privileges hierarchy, instruction hierarchy, you will see that it's optimized for average case. So there is no notion of worst case security for this mitigation right now. And that makes me really worried, and I'm not sure how we are going to get there. So the message here, whatever third parties, even if those are giant vendors which supply the best, the most known existing base models today, that doesn't mean that it has the proper levels of security and privacy already included. So it is still on our shoulders to make sure that applications that are built on these systems are secure. So, and that, again, that it means defense in depth, right? So we have all kind of prevention approaches, but those might be infeasible. We don't have the access to those base models. We can do detection at runtime. And most importantly, I would say the most lightweight defenses that we can think of sometimes will be the most practical, and they will be the most effective because they're easily deployable. So even if this intrinsic vulnerabilities cannot be solved, if we're able to do something easy to counteract these threats, then that's what we should do. I already mentioned before that LLMs will suffer from the same problems that traditional machine learning. So it is possible to reconstruct training data from LLMs as well. And importantly, if the base model was trained for accuracy, for performance, and was not trained for privacy, then by just fine-tuning it on your confidential data with the best practices for privacy, that doesn't mean that the model will not leak anymore. So this is something to keep in mind. And as I mentioned before, differential privacy is really hard to apply. It is very case specific, and in cases of LLMs, it is just infeasible. So we have to resort to something more on a trade-off. We have to do what we can to find a better trade-off. And as I already mentioned, especially in LLMs, if we are able to avoid inputting confidential information into LLM, today it's the safest course of action. So I just have like a minute left. So let me then, I'm not going into more examples of issues, but I do want to mention kind of an elephant in the room. Let me compare the current situation with AI to cryptography. In cryptography, through the years, we have established that there needs to be a proper due diligence process and verification to new cryptographic algorithms. The new algorithms, they undergo scrutiny before they are deployed, before they are implemented in hardware and so on. And this kind of way is much more risk aware. Now, what do we have with machine learning? So there comes some idea, optimization is purely performance focused. Then some companies do implementations. Maybe someone will do a scientific publication, that's not for sure. And they already start deploying, they already start making profit. And then at continuous deployment, the systems might undergo some public scrutiny, maybe not, maybe some incidents might arise, maybe not. And then that already involves damage. But then once the damage happens, of course, there's an opportunity that the application then will go out of business, but I'm not sure if that has ever happened. Then some mitigations are applied and we are back to the start. So I believe the way that we are handling AI today is treating security, privacy, and other aspects as an afterthought. And I think we really can do better because we already showed that we can do better in other domains. And AI should not be an exception. So basically, if we are more proactive, we will already do better than we are doing now. I gave you some examples throughout the talk. I also want to explicitly mention compliance. Understanding how we can comply in our AI system will also be key in the coming time. I also want to explicitly mention red teaming. So this is like the emerging approach to securing AI in practice when we are trying to do extensive security testing. But again, as I said at the start of the talk, I want to help us step out of this box for a moment. So we need to remember as an invariant that top performance will always be in contradiction with trustworthiness. It will continue being a challenge. Security and fairness and privacy will continue being a challenge. So finding this trade-off is really hard. And I just want to say that there's also a secret option C, and maybe we shouldn't use AI for everything. And that is just something to keep in mind. So I will leave you with a few following takeaways. Let's remember that increasing autonomy of AI in our systems amplifies all existing risks. Let's remember that as a rule, and then we will be better prepared. AI and LLMs act as a vulnerable intermediate layer. Even if there is more obscurity, the security problem is still there. These are all open challenges. There is no comfort zone in what I've been discussing with you today. I can't point to one practice and say, if you do this, then you are safe. It's a combination of all these aspects that we have to consider, and we have to do so holistically. So we can't look just at the AI model in isolation. We have to look at how it interacts with the entire system. And if we were able to secure our model against one type of threat, it doesn't mean that protection transfers to other types of threat. So with that, I want to say that as a community, we need to collaborate on all these trajectories to do better. And in the meantime, we need to be more conservative with AI applications in industry. At our university, we do some trainings which are directed towards industry partners, also towards PhD researchers. And we also do a one-year master's, which is also tailored towards professionals who want to do AI and security masters in 1 year or in several years in parallel to their main employment. So please check it out on our website. And with that, yeah, I thank you for your attention, and I will be here for the next 2 days, and I'm happy to interact with you. So thank you again. So I will see you then in the hall.